All right, so here we are, lecture 13a. We're going to do some examples with Bernoulli. And the purpose of this is we're going to apply Bernoulli equation to solve fluid flow problems. And we're going to do this in combination with continuity, although I should note that we have other tools. So here we go. Here are our tools. Okay, typically this is kind of how we do it. This is how I like to do it. We've got tools. We can use Bernoulli geometry, continuity, and manometer. Now, remember, continuity is just a fancy word for mass conservation. Okay, so here's what we have. We have a pipe. The pipe flows, don't know which way it flows. I'm just going to say it flows from A to B. Okay, could go the other way. In fact, with Bernoulli, there's no clear way to tell that for sure. We know that it has a flow rate of 13.2 CFS. That's cubic feet per second. And we know that PA over gamma, okay, P over gamma is 22.1 feet. Okay, that's an expression of the pressure. So basically that means is if I were to put in the piezometer right here, okay, the fluid would rise from point A up 22.1 feet. Okay, I know the diameters of both of these pipes. This diameter is 1 foot, this diameter is 2 feet. Sometimes they use phi. More often than not, you'll see a capital D, and that's probably the way we will usually go. And then we've got this PB right here, okay? So what we're going to do here is, what I want to do is, we've got all of our tools over here, and what I want to do is I want to start by thinking about the Bernoulli and whether or not we can use Bernoulli in this case. It'd be unusual if we couldn't, since this is the class on Bernoulli, but let's think about the assumptions for Bernoulli before we jump in and use it. Okay, and here we go. So 1, okay, is the fluid flow steady? Well, I gave you a Q, and I didn't say the Q was changing. So we're going to go with yes for that. Okay, number 2, is the fluid flow inviscid? Meaning, between our 2 points, A and B, is there a loss of energy due to friction? Or is there gain or loss due to like a pump or a turbine or any sort of mechanical instrument? Okay, and the answer is no. Okay, there's definitely friction there, but we're going to assume yes, because we want to be able to solve this. Okay, what about, and also I haven't taught you how to do with it, so we're always just going to assume yes in that case. Is the fluid incompressible? Incompressible. Well, that depends on what the fluid is. And I didn't really say anything about that now, did I? Okay. Turns out, and I suppose I forgot to put this in here, but this is water. Okay, so because it's water, really, as long as it is a liquid, we can go ahead and with the incompressible assumption. Okay, what about streamline, or my 2 points along a streamline? Well, it kind of depends. If you choose A and B, they're both kind of in the middle of the pipe, so we can go ahead and assume they're along a streamline. Okay, so we're going to choose A and B. So we're going to use Bernoulli, PA over gamma plus, okay, it turns out this will be gamma water, since that's the fluid we're working with, plus ZA plus VA squared on 2G equals PB on gamma water plus ZB plus VB squared on 2G. All right, and apparently when I wrote out the problem, I forgot that we have the elevations of these points. So over some datum, point B is 25 feet above that datum, and point A is 10 feet above that datum. All right, so we're going to go ahead and let's see, which one of these do we want to use? Well, we're using Bernoulli, so let's start seeing what we can solve. Okay, so I know PA over gamma water is 22.1 feet, okay, because that's given. So let's do this in like blue so we can actually see my marks. Well, let's do it in, blue, not highlighter, but just blue. Okay, so that's 22.1 feet because that's given. Okay, let's do PB, unknown, that's what we're looking for. ZA and ZB. I could move the datum if I wanted to. I could make A the datum, and then that would make ZB would be 15 feet. Or, I could, as long as ZB is 15 feet higher than ZA, it doesn't really matter. So let's go ahead and make this one 10 feet. Let's go ahead and make ZB 25 feet. That's how high they are above the datums. And then we've got VA and VB, and we can't really work with those just yet. So those are currently unknowns, okay, because there's nothing given about those two. So we're left with, let's see, 22.1 feet plus 10 feet plus VA squared on 2G equals PB over gamma water, that's what we're looking for, plus 25 feet plus VB squared on 2G. Okay, now note, okay, so notice what I'm doing here, and I've done this before, I'm using Bernoulli as my master equation. Okay, why am I doing that? Well, mostly because it's the only one that's got the pressure B in it. I mean, technically that's in the manometer equation, but we don't even have a manometer, so we can't use that. Okay, we've already used the geometry when we used, so you know, we're just kind of making use of what we're given. Okay, so if I want to rearrange this for simplification, I could make this 32.1 on the left minus that 25, and I ended up with 7.1 plus VA squared on 2G equals PB on gamma water plus VB squared on 2G. Okay, so that's kind of where we're stuck at the moment. To get rid of the velocities, the way that we almost always get rid of them is we're going to use a continuity. Okay, so the continuity equation in this case is actually fairly straightforward because it gave us Q. Okay, so I can use that Q, and I can say that Q equals VA AA, so the areas. Okay, similarly, I can do the same at location B, so Q equals VB AB. Okay, so we'll go ahead and do that. So Q equals VA. That's what we're looking for, so we can plug into the Bernoulli. We don't really want Q, we want 13.2. 13.2 CFS. Okay, AA. Well, AA is pi times that diameter, 1 foot squared on 4. Okay, and we solve for that. 16.81 feet per second. Okay, now I could do the same exact procedure to get VB, but I'm actually not going to because it's quicker, for me at least, if I note that, look, this diameter is twice as large as this diameter, which means that the velocity is going to be 1/4 as big. So basically I can take this VA of 16.81 and you divide by 4 and I'll get 4.20 feet per second. Okay, so now I got my two velocities. Okay, and if you can't follow that, just do this again right here, except use 2 instead of 1 right there. And hopefully you'll see that you get the same answer. Okay, so then we're going to plug it in over here. And so we're going to take those two numbers, plug them back in over here. I'm going to get 7.1 feet plus VA, 16.81 feet per second squared over 2G. In this case, careful, G is 32.2 feet per second squared. We know that because we were working in the English system. PB on gamma water plus VB, which is 4.20 feet per second squared over 2 times 32.2 feet per second squared. Okay, so if we solve this, we get PB over the gamma of water as 11.2 feet. And then PB equals 11.2 feet times the gamma of water, which is not 9810. It's 62.4 pounds per cubic foot. Okay, so notice if we've got a pounds per cubic foot times feet, we'll get pounds per square foot. So that's going to be 8.9, excuse me, PSF, pounds per square foot. Okay, and since it is more common to use PSIs and PSFs, we'll make that 4.85 PSI. Okay, still I prefer this unit. I'm sure there will be engineering times when you need this one, but this is my preferred. Okay, just because it's easier to work with. You know, most of the measurements are not in inches. Okay, so that's kind of how we work it. And I think that's really all there is to say about this one. I will note that, look, PB over gamma W, it goes up to 11.2. So here, let me do a little quick diagram here of what's going on. So as this fluid flow, Let me do a better diagram. I don't like that one. So it's going up like this. And as it goes up, the pipe is expanding. Okay, so the first thing we know is that this is 10 feet and this is 25 feet. So 25 feet, 10 feet. Okay, now we know that we were given PA over gamma water is 22.1 feet. So now we're going to go up another 22.1 feet. 22.1 feet. So this is PA on gamma water. This is ZA. This is ZB. This side on this end, it's going to go up 11.2 feet. So we got 11.2 feet. So that's PB on gamma water. Okay, with the kind of the dividing lines being right in the middle there. Okay, here's our datum. And then so we get up to some point here. So this side we're up to 36.2 over here, 36.2 feet. And over here we're up to 32.1 feet. Okay, and then note that if I were to solve for this term right here, I could do the same for this term right here. Okay, and plug those into the calculator. I get 4.4 feet on this side, and I get 0.3 feet on that side. Okay, then what's going to happen is if I plot those on here, okay, this thing's going to go up here. I'm going to get 4.4 feet. Obviously, I'm not doing this to scale. And right here, I get 0.3 feet. And this would be VA on 2G. This would be VB squared on 2G. And note that these two would be at the exact same level. Okay, so they would add up to the exact same amount. Okay, now why is that? Okay, well that's because PA over gamma water plus ZA plus VA squared on 2G equals PB on gamma W plus ZB plus VB squared on 2G. Okay, so it's these things just, they add up, okay? Now in this case, this means energy is completely conserved, so no energy lost. Okay, and that has to happen because it's inviscid. Okay, so in reality, this line right here, which I just drew as level, we're going to have to lose some energy. So in reality, it's going to have to go down. So there will be an energy loss. Okay, but we're not there yet. Just something to kind of like prime your brain, have you think about it a little bit. Okay, because that's where we're going. Okay, so pretty complicated. Let's go and let's see if we can solve another example. Okay, so over here we've got some sort of tank or something, and it has, it's full of water. Okay, and it is being drained off on the right by this pipe. Okay, and I mean, this obviously, I kind of think of this as the Gatorade problem. I think back to practices when I was growing up, and there was always a Gatorade container. And the more water was in the Gatorade container, the faster the water would come out. But late in the game, or late in the time, as this depth right here increased or decreased, eventually it became, the water would just kind of come out as a dribble. Okay, and so the question we have here is, how fast is this water coming out right here at the moment when this tank is 15 feet deep? Okay. Now, what's important about this one is, well, in a second, when I get the continuity, we're gonna do something very important that's gonna apply very often. But first of all, how do we get this V? Okay, and there's two places where the V exists. Okay, where we get velocities, we get that in the continuity. Okay, and we get that in Bernoulli. Now, my assumption again is that using Bernoulli as the master equation is going to be a good one. We can go ahead and test that. Let's just see if we can use Bernoulli first of all. Okay, again, we want to think about our assumptions. Okay, one, is this steady? In this case, the answer is no. Okay, as this thing drains, obviously, the velocity over here is going to change. Okay, however, we're going to assume it's quasi-steady, meaning that it's going to remain at 15 feet more or less for long enough that we can consider it to be steady. Okay, so that's an assumption, and that assumption is based on the fact that this little opening right here is small compared to this, to the surface of that tank. Like if you imagine if we were draining, say, Lake Tahoe. Okay, so Lake Tahoe, and we just have a little garden hose coming out the end of it. Okay, and the water's coming out of it. Well, this surface is dropping, right? But it's not dropping fast enough that we couldn't consider it to be steady. Like, the surface isn't really changing. Okay, so that's kind of what we're doing. We're saying it's quasi-steady. Okay, how about Inviscid? Okay, can we say that between whatever 2 points we want to use, that there's no friction, there's no turbines or pumps or anything like that? Well, certainly no turbines or pumps, but let's pick a point, right? We'll say the fluid is starting right here, and it's leaving right here at 2. Is it reasonable to say that there's a streamline that goes like this? It seems like that's probably reasonable. But then the question is, I guess that answers our fourth one, streamline. Okay, so we'll go with yes there. But then the question is there any friction loss along that streamline? Okay, and there's, again, as always, no, it's not Inviscid, but we're going to assume that it is because we don't know how to solve it without that at this point, okay? And then the third one is incompressible. Okay, is this incompressible? And the answer is no. I mean, yes, because it's water, okay? Now, the last thing here, and unfortunately I cheated this for you as we solve this, is you might have a question about this, and you might say, okay, I know this is Bernoulli equation, but usually these points are not given. And so you might say, why did I choose these points? And I'll tell you right now as I go through it, okay? Because you are going to have to choose these points. I am not going to be here to choose these points for you. And it has to do with one very simple thing, which is you want to look for points that are attached to the atmosphere. Because if the point is attached to the atmosphere, like point 1 is at the atmosphere, so this right here is 0 gauge, okay? Because it's atmosphere, okay? And that just makes my life a lot easier. So that's what you're always looking for. Okay, this point 2, which I have chosen, is also in the atmosphere because it is exiting that pipe into the atmosphere. Okay, so we can do this one and we can say 0 gauge because P atmosphere. Okay, that makes my life so much easier if we do it that way. Okay, you don't have to do it that way, but it becomes a lot more difficult. Like if I were to choose a point right here, what's the pressure right there? Well, that's a difficult problem because is the water moving? It's kind of moving. It's moving a little bit. It's really only moving when you get close to this entrance. But you need it to be not moving in order to do the hydrostatic assumption. And I don't want to deal with hydrostatics. I just want to solve the problem. So choose the point that's at the atmosphere. It will help you a lot. Okay, so we chose those 2 points. Okay, now we need the z's, okay, the elevations. So what I'm going to do is I'm going to go through right here. Here's my datum. Okay, that's going to make Z2 0 because it's the datum. And Z1, 15 feet, because that's where the surface of the water is. Okay, and now we're left with the velocities. And so usually what we do with the velocities is, well, we can't really solve for them. So we use the continuity equation. But let's go ahead and see what we got. We got 15 feet plus V1 squared on 2G equals V2 squared on 2G. Well, that's kind of nice. That's not too difficult. Let's just kind of leave it like that. And the only other equation that has the velocities is continuity. So I need to get rid of one of these or the other one. So this is an interesting thing that pops up a lot. And there's a simple way to do this, and I didn't do it just now. But what happens is with continuity is if we look over here, we have what I call the Lake Tahoe assumption. I call it either the Lake Tahoe. So sometimes I'll call it the Tahoe assumption. Sometimes I'll call it the tank assumption. But basically what it boils down to is And suppose this is the area of the hose, This is the area of the lake. Okay, so I want to do continuity on this little, on this Lake Tahoe thing. Okay, so I've got a certain amount of fluid flowing out right here. Okay, so that's Q out. So I'm going to do in equals out plus accumulation. Okay, I'm going to draw a control volume that looks like this. Okay, there's my control volume. Okay, so what's flowing into that control volume? Well, it's whatever is, all this stuff that's flowing down into that control volume. Okay, so that's going to be Q in, I guess, equals. Now what's flowing out? It's whatever's coming out right here. Q out. What's accumulating? Well, based on what I drew, where I drew my control volume, nothing's changing. Okay, because I decided to do this in the way where you put the control volume below the surface. Okay, so now I've got that, and what I can do here now is say Q in. Well, what's Q in? So that's going to be V in, A in equals Q out. Well, that's going to be V out, or VH for the hose, I guess. If it will let me erase, it hates erasing. VH, AH. Okay, so then I can go, okay, well, V in then, and that's ultimately the rate at which the lake is dropping, equals VH times AH over AN. Okay, but what's AH over AN? Well, AH is the cross-sectional area of the hose. So, let's suppose you got a little garden hose. Maybe that's a square inch. And what's the area of a lake? So maybe this is a square inch. So maybe let's put it at 0.01 square feet. What is this one? The area of so the area of the surface area of Lake Tahoe or a tank or something. Well, let's suppose it's let's make it a small lake, 1,000 square feet, right? So 1,000 square feet is, what is 1,000 square feet? Is that 60 by 60? Okay, so it's really just a pond. But look at this ratio here. Okay, so 0.01 divided by 1,000 is 10 to the minus, this is 3, that's 2, so 10 to the minus 5. Okay, so Vn basically is approximately 10 to the minus 5 times the velocity coming out of the hose. Okay, which basically means usually when we use the tank assumption, what we're going to do is we're going to assume that the velocity of a tank or the velocity of a lake, the velocity of a Tahoe equals 0. Okay, we're going to assume that because it's very, 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 very small, and it's very, very, very small in comparison to this one. Okay, because if we go up here, and if I plug these terms in, they're getting squared, and so it's going to make that 10 to the minus 5 a 10 to the minus 10. So it's really going to get even smaller and smaller and smaller. Okay, so what we're going to do up here is this V1 right here. Okay, I'm going to call this the tank or the Tahoe, or use just like a tank assumption, is that I'm going to assume that this is very large compared to this opening down here. And so when I do that, what ultimately I'm going to do is I'm going to take V1 and I'm going to make it go to 0 because of the tank assumption. Okay, it's very important that you understand that because we're going to do that a lot. Okay, which means now I can solve for V2, which is what we're looking for in this problem. Okay, so 15 feet equals V2 squared over 2, and in this case it's feet, so we want 32.2 feet per second squared. Okay, so V2 ultimately equals 31.1 feet per second. Okay, and that's how you solve that. And that's a very important assumption that you need to be aware of and be ready for it to show up anytime. Okay, and it's going to show up so often that hopefully you'll kind of get used to it. At first, it might make you a little uncomfortable. Okay, so we're going to go ahead and break off, and we're going to go to the second part of this. Oh, I should note, just in case you're wondering, well, what happens when take this number right here. What would happen later, like the Gatorade problem, when that thing gets a lot smaller? So let's suppose we had 1 foot equals v2 squared on 2g. Okay, it should be clear already that the velocity is going to be much less. It's going to be 8.02 feet per second. Okay, so basically as this drops, the velocity is going to keep getting less and less. Okay, if that were 0, obviously the v2 would be 0. Okay, so that's kind of a nice result. All right, anyway, we're going to go ahead and stop here, and we'll come back and I'll do part B.